Good evening everyone. Today we are discussing regarding bridges. Bridges are the circuits which is having two parallel branches, and a detector is connected in between the two parallel branches. They look like this. In this way it will look like P, Q, R and S. P will be the unknown resistance. To find this unknown resistance, a variable resistance is varied such that the balancing circuit balance will occur. The balancing will be taking place when VA is equal to VB. At this position, the deflector becomes 0 such that the ratio at this point we will derive a condition such that we can measure P with respect to QS and R. At a potential A, at the bridge balance condition, the current flowing through this is 0. When we use voltage division rule, that means total voltage is E into the voltage VA will be the voltage across this Q. So Q by P plus Q. This is voltage across this point A, VA. At voltage VB is total voltage into same resistance by sum of resistances. Anywhere in the circuits, if you wanted to find a voltage across any resistor, means the voltage will be on that resistance. The voltage at this point is nothing but voltage across this resistance. If you want to find a voltage across here, then this will be the voltage across this end here. Now E cancelled. Q by P plus Q is equal to S by R plus S. Then Q R plus S is equal to S into P plus Q. QR plus QS is equal to SP plus SQ. And here we can see this QR and SQ are same, so they are cancelled out. Therefore QR is equal to SP. So here is the P is the resistance and this is the S, and Q and R. We can write P is equal to QR by S. In this way, with using Q, R and S, we can measure this P. Simply we can write PS is equal to QR. PS is equal to QR. Now with the help of this bridge balancing condition, we can measure resistances, inductance, capacitances, mutual inductance and frequencies. These all can be determined using this bridge balancing condition. Here detector. Detector is nothing but which sends the voltage or current in the circuit. Example, galvanometer. And for easy way, galvanometer is used, and other are headphones. Headphones are nothing but when in frequency is applied within some frequency F, current is applied in this detector, then it's due to that frequency it produces an vibration and that converts into sound. So those are can be used, and etc. This is the typical bridge calculation, and when we are going to find the inductance, capacitance, frequency and resistance values, then there are different types of bridges. Those will be explained. There are two types of bridges. One is AC bridges, second one is DC bridges. Now we are going to discuss AC bridges first. Later we will be discussing DC bridges. First we will be seeing the difference between AC bridges and DC bridges. So we will see how the AC bridges will be there, how DC will be there. For AC bridges, we will call the elements are impedances. This is Z1, Z2, this will be Z3, Z2 and Z4 at an angle theta 1, at an angle theta 3, at an angle theta 2, at an angle theta 4. An input AC voltage is applied, V in. For this, bridge balancing condition will be, first we will be writing magnitudes Z1 into Z4. Z1 into Z4 is equal to Z3 into Z2. This is the magnitude, and when coming to phase, theta 1 plus theta 4 is equal to theta 3 plus theta 2. This is the phase angle balancing condition. Similarly, for DC, there will be only resistor circuits. A detector, R1, R2, R4, R3. So for this bridge balancing condition is R1, R4 is equal to R2 into R3. And we have detectors. Detectors for AC. AC bridges are vibrational galvanometer. This is between 5 Hz to 200 Hz. If it is below 5 Hz or nearer to 1 Hz, like, then DC bridges are preferable. Telephone detectors. This is between 200 to 5 kHz. Telephone detectors are when this amount of frequency current is applied, then they makes a sound such that it indicates that bridge is balanced condition or not. Like toned amplifiers, it is greater than 5 kHz. These are used when the circuit containing greater than 5 kHz operating conditions. For DC bridges, galvanometer is used. DC bridges can measure only resistances. AC bridges can measure inductor, capacitor, mutual inductance, resistance and frequency, etc. Now these are the differences for AC bridges and DC bridges. Now we will be moving on to our first topic, AC bridges. In AC bridges, we are going to discuss first one, measurement of inductance. It's a self-inductance. And next we will be going to learn about measurement of capacitance. Third, we are going to learn about measurement of frequency. These three we are going to discuss in this topic. After we will be doing few problems. Before starting AC bridges, the terms you need to know is quality factor. The quality factor is the measure of how good an inductor or a capacitor in a circuit while storing the energy compared to losing the energy. It is a measure of how good or efficient the inductor or capacitor is at storing energy compared to dissipating or losing it. Formula for Q will be 2 pi into energy storing in a coil divided by energy dissipating in a coil. Practical inductor is having Z is equal to R plus J XL. That means there will be a resistance. If resistance is high, then dissipation of energy will be more rather than storing the energy. So Q value will be less. When XL value is more, then storing capacity will be more, then the Q value will be increasing. The formula for Q is, for in inductor, Q value will be omega L by R. In capacitor, Q will be 1 by omega C into R. If Q is higher, then it is selective. That means if we need 93.5 megahertz, then a higher Q value inductor will allow only 93.5 megahertz signal. That is the usefulness of high Q value. Typical Q value considered are when Q value is less than 1 and Q value is between 1 less than Q less than 10 and Q is greater than 10 is considered as high value. This is medium value and it is low value. Now first bridge circuit, that is in the measurement of inductance, this is the first circuit which measures the inductance value. This is the L1 R1 is the inductance which is to be measured by varying R2 and L2. So the current flowing in this circuit is I1, the current flowing through this line is I2, and the potential between this point to this point is E1, and this point to this one is E2, E3, and the potential between this point to this point is E2, and this point to this point is E4. So E1, this to this is E1, E2, E3, E4. In this we are now going to find derive this circuit in 3 steps. One is circuit diagram, another one is phasor diagram, next bridge balance condition, and obtaining the inductor and resistor values. Next step is phasor diagram. Phasor diagram. So in this we will be assuming I1 as a reference. As we can see, both branches are identical, so I1 and I2 will be are in the same phase. Same phase means they will be operating in same frequency. These phasor diagrams are drawn on the basis of same frequency. There is no phase shift. I1, I2 will be in the same phase. Now in this branch, I1 current, when under bridge balance condition, I1 will be flowing in here also the current is I1. In this current also I2. Therefore here we can say I1 R3, and this voltage drop will be equal to this voltage drop, that is I1 I2 R4, that is E3 is equal to E4 at this point. So now E1 and E2, E1 having resistance and inductive drop. So resistance drop with respect to inductor will be 90 degrees. 90 degree it is in 90 degrees form. If I1 R1 is here, then the drop related to I1 omega L is 90 degrees perpendicular to it. Then the resultant will be E1. So in this E1 and E2 are equal at the bridge balance condition. So this will be equal to I1 and Z1. We can tell this is I1 and Z1 and Z2 also. So at this point I3, E3, E4 and this point E1 and E2, the resultant will be this will be the total voltage. Now from this, third step is bridge balance condition. Balance condition is Z1 into Z4 is equal to Z3 into Z2. That means Z1 is R1 plus J omega L1 and Z4 is R4, Z3 is R3 and Z2 is R2 plus J omega L2. From this we need to find L1 and R1. Now multiplying all of them inside. Now comparing real and imaginary terms. Imaginary on both sides. That means real terms are R1, R4 is equal to R2, R3. From this we can write R1 is equal to R2, R3 by R4. Here imaginary terms are J omega, J omega. That means omega L is equal to omega L2 R3. Therefore omega omega cancel. L1 is equal to L2 R3. Sorry, here R4 is missing, so here R4 will be written, we will be returning. So R4, here we can write this is the L1 term and this is the R1. Now we are going to discuss Maxwell inductance capacitance bridge. In this the inductance is measured using a variable capacitor. First we will be discussing these circuit parameters, next phasor diagram, next balancing condition. So the current I is flowing in the circuit, it divides into I and I2. At bridge balancing condition the current across this, the inside this is 0. So the current I1 is same as the current going here is 0, so the same current flows here I1. Here the two currents will be dividing. Here going current is 0, so entire I2 will flowing here and it divides into IR and IC. This is IR current, both combining to form again I2 and I is coming outside. So this is V in, AC input voltage. Now for this voltage drops are E1 and this is E2. This totally, this drop across this is E3 and the drop across this resistor is this is E4, this is E3, this is E1, this is E2. Now phasor diagram. Now phasor. From this we will draw a reference line I1. This is the current I1. In this first drop we saw is I1 R1. I1 R1. The inductor drop is J omega L. That means 90 degrees to the resistance. that is I1 omega L1. So the resultant will be total voltage E1. This E1 is equal to E2 in the bridge balancing condition. That means E2 will be I2 R2. Now the coming to this branch E3 and E4. E4 having two parallel branches, one is IR and IC. Now we will take IR as a resistive. So IR is in phase with as it resistive circuit, it is in phase with it. So IR with respect to this, IC will be 90 degrees. Comparing to the resistive element. Now the resultant IR and IC will be I2. So we will be drawing the I2. We will extend this. We will extend this such that this is the drop for I2 R2. It will be equal as those are in same current. The drop on this is same. So this will be the I2 current. Now we need to find E3. E3 is the drop of I1 R3. This is the E3 drop. This drop is equal to IE4 drop. This magnitude of this is equal to this. This drop is equal to IR R4 and IC 1 by j omega C4. So this point is E3 E4. This point is E1 E2. The resultant will be here. That is total applied voltage E or V in. Any way you can call. Here we can take it as E. At bridge balance condition, Z1 Z4 is equal to Z3 Z2. That means Z1 is R1 plus J omega L1. Z4 is R4 in parallel with C4. That can be written as R4 into 1 by J omega C4 by 1 plus R4 plus 1 by J omega C4. If you take an LCM, then it can be rewritten as 1 by 1 plus J omega C4 R4. Then in place of this is Z4, here we will be writing the same expression, J omega C4 R4. Z3 is R3, Z2 is R2. Now multiplying this here, and R1 plus J omega L1 into R4 is equal to R2 R3 1 plus J omega C4 R4. Splitting the terms, R1 R4 plus J omega L1 R4 is equal to R2 R3 plus J omega R2 R3 R4 C4. Then comparing real and imaginary terms. Real terms are R1 R4 is equal to R2 R3. Imaginary terms are L1 R4 is equal to R2, R3, R4, C4. Therefore R1 will be R2, R3 by R4, L1 will be R2, R3 and C4. This bridge is used for inductors with Q value from 1 to 10. It is an measuring. It is an instrument to measure at power and audio frequencies.